Okay, students, let's get going with lecture. You guys ready? I wish I had an eraser that I could throw to people in the second row. Shh, 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 shh. Let's get going. All right, a couple things I want to mention to you before we start the regular part of lecture. 2 weeks from today is November 20th. We'll have exam 3. And after exam 3 is graded, we will have best 2 out of 3 maneuver. All right. Now, it sometimes takes me a couple days to get everything to the point where I do the best 2 out of 3 maneuver. But when I do, I'll put a new row in the grade book, in your grades page, and it will indicate what your best 2 out of 3. Now, some of you have missed an exam 1 or exam 2, and you got to be here for exam 3. Otherwise, you won't have best 2 out of 3. You'll have whatever you have, okay, because we don't have any makeup exams, all right? But if you missed exam 1 or exam 2 and you make it to exam 3, then we'll keep the 2 grades that you've got, because the one that you missed is going to be your dropped exam. Now that holds whether you're excused or unexcused. Okay? That's the common maneuver for missed work, for missed exams. And just to reinforce, Maria, what was the next Tuesday? Next Tuesday you will not be here? Okay. Oh, so you'll be in your SI sessions? Okay, so normal SI next week. Okay, we're going to talk about oscillations and stuff. This is chapter 7, I believe. But before we get into that, let me just do a public service announcement. Make sure you get to vote today if you haven't already. I'm going to be blazing out of here right after class and dash back home and cast my vote. So I urge every one of you to do that as well, if you haven't already. Okay, chapter 7, oscillations. Hold on. Let me turn off my phone so that Siri doesn't start getting notions. This is a image from your textbook of a perspective view of the Arctic Ocean and North America mainly, and the North Atlantic and the North Pacific. This is a picture that shows what they call the Arctic Oscillation, which is a weather pattern. You know, it's interesting. I was reading this article in, I believe it was in Geophysical Letters, which is about geophysics, a number of years ago. And they had this one summer when the Arctic ice cap was gone. During the summer, it was open water at the North Pole. And everybody's saying, oh, global warming and stuff. But it ends up, they studied the weather pattern, and apparently that summer and that spring, there was a persistent weather pattern from Siberia that blew almost all the ice cap, which is susceptible to motion in the wind, and it piled it all up by Greenland and northern Canada. So there was a lot but it wasn't like melting up there. It was just dislocated out of the way. because ice is movable. But this is another weather pattern. This is the Arctic oscillation. And a couple things I want to bring out to you from looking at this diagram. First of all, it is enormous. It is an oscillating system in atmospheric pressure, average atmospheric pressure. So this picture reflects zillions of pressure measurements made in the atmosphere over the course of many, many days between oscillations. And high pressure is over here on the left, this brownish area. Get my cursor. Okay, so this area over here, and then this kind of purplish area in the second image, that's the lower pressure variation, and that affects the weather and all the things that are happening up there in the Arctic, and very difficult to model. But look at the size of it. If you look at the picture, you'll see down right here, you'll see Hudson Bay in northern Canada, right? And then here's Greenland, and all the way over here, this little edge at the very top of the sphere, that's Siberia. That's eastern Siberia in Russia. Okay, and then around over here is Alaska, and you can make out here's Greenland, and then way down here, this is Africa. Here's Florida down here. So we got half the Earth visualized in this. This is like a picture from a satellite. It's artificially made, but they make it look like, a certain elevation, looking down on a certain part of the Earth. Here's Europe over here. This is Siberia. This is Norway, right here. So Scandinavia is right up here. Here's England and Scotland. And here's Iceland. It's an amazing map. So this is enormous atmospheric oscillations. And it's enormous spatially, and it's pretty big temporally as well. It's got a period of oscillation measured in months. This is not day to day. This is month. This is over the time scale measured in months. And so when you're looking at oscillating system, its spatial variation, its temporal variation are both important. How fast does it oscillate? How big does it vary, from high pressure to low pressure? Okay? And we're going to study oscillating systems, some basic ones. The first basic one that I want to study with you today is just uniform circular motion. We've already studied this. We know that the centripetal acceleration for uniform circular motion is v squared over r, because the speed, v, is a constant if it's uniform circular motion. Now, if you're on a circular track at Nardo in southern Italy and you're speeding up or slowing down, that's circular, but it's not uniform circular. But you go to the Nardo ring and you turn your vehicle cruise control on to whatever you want it to be, 110 miles an hour. That'd be pretty cool, operating a car, for 6 hours at 110. Just letting it go, baby. And listening to music and stuff. That'd be pretty nice. So constant speed, but not constant velocity. Constant radius from the center, circular. And here, this one is 300. This is a 300 pixel diameter circle. And go ahead and park kind of a generic point up here in the first quadrant. Don't pick any special, so don't go up to 45 degrees or anything. Just kind of put it up there somewhere. A little bit out to the right and almost to the top. Not quite. And so here's a picture now. All right, so there's my x and y coordinates. And that's a generic point. And we're going to talk about this entire circular path. This is a graph of the x coordinate, the horizontal component of the motion, over time. So the time axis is down here. It's written in with numbers on the bottom part of the graph. Usually we put those up here in the middle, but in this software it puts it in the bottom. And then up here on the vertical part, it's 300 pixels to the right and negative 300, that's 300 pixels to the left. All right, and so what we would say in uniform circular motion, and you can get really fancy with the calculus equations and the trig, but this picture is good enough for us. It has an even oscillating x coordinate. All right, and so for this one, it starts out down here at time t equals 0, left side of the graph, and here's where it starts, and then it gets big up here to 300, etc. Then it dips to the left, and here it is at negative 300 all the way to the left, and then it goes over here. Now, the other coordinate also varies. Here's what it looks like. This is in red. It's the y coordinate. Go ahead and hey, you guys, sketch these in real carefully as you can. All right, because I'm going to ask you some clicker questions about these graphs. And I'll blow them up a little bit bigger. This is the vertical y coordinate over here in red. And this one starts out a little different, but it dips and then rises and then dips again and then rises. And both of these graphs represent 2 full cycles, 2 trips around the circle. All right, now if you don't believe me, just look at the y coordinate. It starts at 300, goes back to, it goes down to left 300, minus 300, back up to 300. Okay, so that's 1 full circle to here. Then it dips back down all the way to the left, negative 300, and then up here, back to positive 300. So that's a second full circle, right? And the same thing over here. This one's a slightly different shape, but here's 300, and here's another 300. Here's a minus 300, and here's another minus 300. And so this one's going through 2 full wiggles. Vocabulary term. And this is not a physics term, it's a physiology, cardiology type term. You could use the word sinus rhythm. Have you ever heard that? You know, you're watching some TV show and the emergency guys come in and, somebody's feeling, okay, we got a sinus rhythm again. Their heart's defibrillating and stuff. And sinus rhythm means that, and almost everybody in here looks healthy. Well, almost everybody in here. Some of you guys, I don't know, but no, everybody looks good. Everybody in here, if we put you up, hooked you up to EKG, and you weren't like looking at a monster movie where you're getting frightened half to death every 5 minutes, what would happen if you got frightened half to death twice in a row? Does that mean you'd be completely frightened to death and you'd be dead? Is that what that means? Anyways. So if you're not doing something that's, like causing a fright or something, you're going to have a nice, easy sinusoidal rhythm in your heartbeat, your EKG. And so sinus rhythm that's what they would call it physiologically. And in physics, we call it a sinusoidal curve. It's from It's from Arabic, sinusoidal, sinus. Sinus rhythm, that's Latin, but it's Latin that was derived out of out of an Arabic word for curve. All right, now I'm going to ask you some brain burners. Get your clickers ready. I've got mine ready. Get them turned on. Frequency DD. Zuckerman, are you here? Sweet. Okay, you ready to click? And, look, just double check here's the graphs again, a little bit bigger. Okay, there's horizontal, and here's vertical in red. And hey, you guys, the horizontal. So just double check, horizontal axis, that's time. And they're all laid out. So kind of make some notes. Try to make it look like this. This is done nicely with a computer. Just do what you can. And I'm going to be asking you some questions about this. Here's another one. And the x-coordinate graph, the top half, it corresponds to positive numbers, corresponds to the right half of the circle. And the negative numbers correspond to the left half of the circle. So half of its time is spent on the right half of the circle, and half of its time is spent on the left half of the circle. Similarly, the y-coordinate down here, the top half of the graph, so 0 to 300 on the graph, corresponds to the time when it's up in the upper half of the circle. And similarly, the lower part of this graph corresponds to the time when it's on the lower half of the circle. So if it's uniform circular motion, it's going to spend half of its time in the bottom half of its time in the top half. But wait a minute, it's going to spend half of its time on the left half and half of its time on the right half. So does that mean it spends twice as much time per circle? No, it just means that if you're on the right half of your time on the right, so a quarter of your time is in the bottom half and a quarter of your time is in the top half. So the northeast quadrant, that's a quarter of your cycle. Southeast quadrant, that's another quarter of your circle. Southwest quadrant, that's down here, that's another quarter of your full circle, your full cycle. So each quadrant takes up 25% or occupies 25% of your time. All right. Now, hopefully you have these graphs done. Here's the, this is the big graphs. All right. And make sure you have the spatial interpretations, right, left, top half, lower half. Okay. And now I'm going to ask you a clicker question. All right. So make sure your clicker's on. Base frequency DD. And here you go. Now I want you to think. There's the two graphs. Here's the starting point for each graph with the arrows. What are the starting coordinates? What comma what? What do the graphs tell you? And this is kind of a brain burner. You guys are doing good, but the next question is going to be it's not a brain burner, it's going to be a brain blowtorch. I'll have to get a special fireworks license for the next question. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, pretty good. You guys got it. 0, 300. That's because the x-coordinate over here at the on the left side of the graph, that's t equals 0. So for the x-coordinate's at 0. The y-coordinate's all the way up here at 300. So 0, 300. All right, now, let's go back to the circle, and you can modify your circle or add to it now. So blow up of it. So you could put the starting point up there. All right. So for those graphs, this is the starting point. Those graphs represent a system where you start your stopwatch when it's at 12 o'clock. Okay, you're watching this thing go around, and you start your stopwatch when it's at the 12 o'clock position. All right? That's what those graphs represent. Now, if you started it at 6 o'clock, you'd have a different bunch of graphs. Okay? But they look similar, but it wouldn't be the same. You know, the curve, the sinusoidal or the sinus rhythm would be shifted left or right a little bit, but it'd still be reminiscent of what we were just looking at. Now, so the start of the first trip around the uniform circular motion is up here at this red diamond. All right, good. Now, a little bit later, or maybe quite a bit later in the first cycle, it gets to this point. But hey, guess what? If this is a snapshot, it doesn't tell you, I've got to tell you what the time signature is on your snapshot. It just tells you where it is. It doesn't tell you, when it is. Okay? So the question arises, how early in the cycle is this other point up here in the northeast quadrant, quadrant 1? Is it in the very first quarter of the motion, or is it in the last quarter, almost done? Almost through the entire cycle, so you're in the fourth quarter of the motion. Because we know it starts there, but is the motion clockwise or is it counterclockwise? If it's clockwise, then it's in the first quarter. If it's counterclockwise, that means to get there, you have to go through all the way around the horn, the long way. So that means it'd be in the fourth quarter if it's counter. So here's our next question, and this is the one that I want you to, it's a simple question, but I want you to think very carefully about this one. Is the motion clockwise or counterclockwise? And just for comparison, here are these arrows for reference show you the end of the first cycle in the x-coordinate and in the y-coordinate. Okay? So that's at about 0.2 something seconds. I think it's about 0.286 seconds. So the question is, does this mean, what do these graphs tell you? Friends, Romans, and countrymen. Good, I see people kind of making signs like this in the air and stuff. Yeah, definitely talk it over with your neighbor. This is a... If you have a neighbor. If nobody's sitting next to you. You guys have neighbors. $20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. You guys did pretty good. Yeah, the start is 0,300. Okay, so and then at that position is a fairly small amount of x. It's the way I had it. It's at like about the 1 o'clock position, so it's barely a little bit over to the right. So that means the x coordinate is going to be up here, and the y coordinate is, it's on a circle, so it's not at 300, but because it's at 1 o'clock, it's going to be pretty close to 300. So that means it's going to be over here somewhere. So there we go. I'm burning them in there. All right, so that's my. Now, based on that, you can make an assumption that the motion is clockwise. All right. So the answer to this one is clockwise. Now, I want you to. You've got a question about why, right? Yeah. Okay. Hold your question, because I'm going to ask everybody. Just listen to what the students, your classmates say. I want you to raise your hand if you voted for clockwise, and if you can, if you voted for clockwise, and if you want to give your reason, your explanation for why it's clockwise. Raise your hand if you want to try that. I see one person, two people, one over here, nobody in the center. Was that you were raising your hand? Do you want to try an explanation? Okay. I want you to listen to the explanations. We got a couple people. Anybody here in the center? The center must represent. Come on, somebody be bold. Bold and crazy. Okay. All right. Now we'll start over here on the right with Rachel. Rachel, speak. You raised your hand. Was that fake out Dr. B day or what? You want to go ahead and give your explanation. And speak loudly enough so that I can hear it. Don't worry about, it might not be perfect, but between all of us, we're going to get a fairly good handle on it. And what's your name again? Natalia. Natalia's going to be listening here, and the rest of everybody's going to be listening, and we're going to put together a fairly good explanation of why it's clockwise. Go ahead. So you just looked at the x coordinate, and it started to the right. And actually that's not bad. That's all, because if it was going counterclockwise, it'd be going to the negatives. It'd be dipping instead of rising. No, you don't get to say anything yet, Natalia. You got to listen to the rest of these guys. It's all right. Now, go ahead. What is your first name again? Alex. Alex, go ahead.
Okay, so on the x graph, as it's moving up, x is increasing, so that means that it has to be going to the right, which would be going clockwise.
Okay, that's kind of what Rachel said in the back. So you're looking at x going positive.
And then the y is increasing, so that means that it's going down, so it's going clockwise.
Okay. Okay. So it's decreasing value of y. Okay. Good. Now somebody over here had their hand up. Go ahead. What did you look at? Okay. All right. So basically the same as Alex and Rachel. Anybody else have a different explanation? Because there's, what Rachel and Alex and what is your name again? Logan. What Logan and Alex and Rachel said is different from what the students in the 9 o'clock lecture said. And you guys are good. I mean, what you said is good. It's righteous. And the 9 o'clock section, what they said was righteous. They just had a different way of saying it. Natalia, what do you have to say now?
I have a question before I can answer that.
Go ahead.
So, you know how there's like the right and then the left, meaning like the upper and then the lower, like on the other graph? Is that only where it starts or is that throughout?
That's throughout. So whenever you see a positive number, whenever this black curve is in a positive region, like up here, or skip over here, that means that corresponds physically to being on the right-hand side of the circle. Now, but half of its time, it's dipped. So down here, the black curve is negatory. And so what that means is that it's over here on this side of the circle. All right. Now, the same thing holds for the Y. That's upper half. And it looks like upper half and lower half for this one. But the black curve, you got to interpret it. Okay, upper half of the graph means right side. Lower half of the X graph means left side. Okay, good? Natalia, speak. Sprechen Sie.
It goes from the right side to the left, but when it's at the right side, it's upper. So then when it goes to the left side, it's lower, right? So wouldn't that have to do with it, or is it more number based?
When it goes to the left side, it's lower. Yeah, actually, that's good. When it's on the left side, it's when it cuts left for the first time, negative in the black curve, it's negative for the red curve. Okay, first negative is here in the black curve. And yeah, definitely. Sweet. So that's another good way to look at it. When it first, so here's the X. So this is going around the horn. This is going down at the 6. So what you're analyzing, see, this is exciting. Listening to you. No, I'm serious. I love this because, everybody, thinks, oh, this is a stupid class and I got to take it and stuff. And that would be true if it was a stupid class, but you guys are not stupid. And this is thrilling for me to bring this stuff out. I mean, it's lovely. I love this. And, this is the thing that we do, So you're looking at the 6 o'clock position. The 6 o'clock, it's dipping, it's in the bottom half, and it starts cutting left. And if it's cutting left at the bottom of its motion, ding, 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 that means clockwise. So that is great. Great. And, do you guys, you want to say something? You're more than welcome to. No, I mean, what do you think?
So from what I'm understanding is if it starts there and it's lower and then it goes to the Y, it's like upper and it's clockwise, and then so the Y is lower and the X, I don't know.
Well, here's how Natalia answered it. She said, look, at this point here, it's cutting to the left. Okay, whenever it's negatory, it's cutting to the left in the black curve. And then that's somewhere between 0.1 and 0.2. So in terms of the red curve, 0.1 and 0.2 definitely is negatory as well. So over here, that means bottom half of the motion. Okay? And over here, that means, in here, between 0, so this is leftward motion, right? So bottom and leftward, clockwise. All right? Now, this is where I want to challenge your mind by saying this. That original picture that we were looking at, this thing, all right, it's kind of, we didn't have any velocity vectors in there. Now we could write one in. It would be up there up at the starting point, it would be straight rightward. Okay, and at the generic point, the black diamond, it would be kind of down and to the right. And that would represent clockwise motion. You can't tell it from this diagram, but you can tell it from these diagrams. And for that reason, I want to emphasize that these graphs also encode the velocity. And so you can add that to your notes. And let me just challenge you further. They completely encode. There's no approximation. Everything is complete. You could, from these graphs, you could calculate the exact velocity. You know, so many meters per second rightward or leftward, so many meters per second upward or downward at any point in time. Now let me ask you this, and this is not a clicker question, although I should have made it a clicker question. Here it is. Here's my question. Looking at these graphs, what feature or property of these graphs, now remember you're thinking x and horizontally and temporally in the first graph, the black graph, vertically and temporally in the red graph, which property of these graphs tell you the speed, the delta x over delta t, that's Vx. Delta y over delta t, that tells you Vy. The two of them give you an arrow, a vector. What is it? Okay, I see a hand back here. I want you to think. I'll get to you in a second. What is your name? Daniel? Okay, Daniel. Anybody else have an idea? What is it that, Rachel, I see your hand back there. What physical or what geometric property of these graphs tells or allows you to calculate a delta x over delta t for Vx, or a delta y over delta t for a Vy? I got somebody in the middle, Daniel. I got Rachel on the right, but I don't have anybody on the left. Sawyer, I don't have anybody from your section over there. They're slacking, I guess. Over on the left, what do you think? What part of the curve, or what property of the curve, encodes velocity information, either delta x over delta t or delta y over delta t? You know, delta x over delta t on this graph, delta x is a vertical and delta t is a horizontal. And on the y graph, delta y is vertical and delta t is horizontal. Daniel, what is your theory? Yeah, it's the slope. Delta x over delta t is rise over run on the black curve. Go ahead and write that down. And I plotted these curves from a spreadsheet program. So I have every point on the black curve, 2 coordinates for it, and I have every point on the red curve, the y coordinate and the time for it. And from those, you could figure out delta x's, delta y's, delta t's. So the velocity, and you know what would happen? Daniel and Rachel and everybody, if you calculated delta x and delta t, and then the corresponding delta y over delta t, and then drew a little arrow in, and it's probably going to be a slanted arrow, so you could do Pythagorean theorem and then do the square root, a squared plus b squared equals c squared. What you would find for these graphs is that v the sum of the squares of Vx and Vy, square rooted, V would be a constant. Vx and Vy would not be constants, but the length of Vx comma Vy would be a constant. And why is that? Because it's uniform circular motion. All right, so all that information is encoded into these graphs. Or you could say it this way. The coordinate information allows you to calculate velocity information if you have coordinate over time. One more thing. If you calculated the acceleration, oh my goodness. It would be an arrow, and guess where the arrow, so you'd get a subscript x and an a subscript y, and guess where that arrow would point? Directly to the center of the circle. And why is that? Centripetal acceleration. So it's all encoded in these two graphs. Matter of fact, I think tonight when you guys are doing your homework, what is it, homework 18 now? When you guys are doing your homework 18, I might do that. Let's see if I can show it to you on Thursday. All right, so we're going to do some more clicking, but for right now, let's do an outline. Here's our question. Why do physical systems oscillate? The simplest physical system is a good old spring. And if you've ever been in a car with bad shocks, or the shocks that are blown, then you know that you go over a bump or even get in or load something in the back, and it'll go, market will just go up and down like this, for a few seconds. All right, it'll just oscillate up and down, spring system. And there's all kinds of spring systems. And one of the things about a spring system is, if you have a spring just sitting on the desk and it's just laying there, it's not going to do anything. But if you anchor one end of it down, you nail down one end of it, and you stretch it to the right, you nail down the left end of it, and then you stretch it to the right, it's going to pull back to the left. But then if you compress it, if you squish it and make it shorter, it's going to push back to the right. So it depends, and it also, the more displacement you have, the more squish down or the more elongation you have, the more pullback force or pushback force you have. Okay, so it's proportional to the displacement from the equilibrium position. So you put the spring down on the table, you nail down one end or fix it to a screw or the side of the wall or something. And the length might be, 12.7 centimeters. Okay, that's your equilibrium length. If you elongate it, it's going to pull back to the left. If you compress it, it's going to push back to the right. Okay, and the more push, you get more push for more centimeters of displacement. Okay, so it's proportional to x. Okay, and if you push one way, if you displace to the left, you're going to get pushback force. If you elongate to the right, you're going to get pullback force back to the left. So that's what we call a restoring force. No matter how you move it, it's going to pull you back towards equilibrium. It's going to try to restore equilibrium. But a spring system is just going to go like this. Boing, 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 boing. It's going to just keep going back and forth. Unless you have some friction. Eventually the friction it'll die out. Or if you have shocks. And shocks is not friction, but it will calm down an oscillating spring system. Okay. But restoring force is how we do that. So now up here, if you're at the equilibrium position, x0, in this first diagram here, then you don't get any push or pull from the spring. It's just kind of sitting there. So you take your spring, you lay it out on the table, you anchor the left end, you put a weight to the other end, to the right end, but you don't move it anywhere, you just attach it. It's not going to go anywhere. It's just, it's just going to be sitting there. No push, no pull. But if you blaze it out to the right a little bit, like over here, okay, to this X position, if you're out there, you're going to get some leftward pull force back toward equilibrium. So if X is positive relative to equilibrium, the force is negative. So you'd have negative newtons. If X is positive 0.205 meters, then your force might be negative 5.7 newtons, depending on the spring. All right? But it'd be leftward, and we would encode that with a minus sign. Now, if you do compression to the left of equilibrium in this diagram, and I don't have this diagrammed out, but you can think about it. If I make my X a little bit to the left of equilibrium, then you're going to get a pushback force to the right, because the spring's compressed and it's going to want to get back towards equilibrium. It's going to want to get back to its relaxed position. All right? So that's what it means to be a restoring force. No matter which way you go, you get some force back towards equilibrium. All right, now the way that shows up in an equation is this, that the force is equal to some constant K times the displacement, and there's a minus sign in front of all of it. Now, the minus sign accounts for the fact that it's a restoring force. If you push to the left, X is negative, your pushback force from the spring is rightward, positive newtons. All right, so negative of a negative is positive. If you extend the spring to the right, X is positive, you're getting a pullback force from the spring. It's negative. Right? Negative times positive, negative. Right? So F equals minus Kx. Anytime you see a system where the force is minus some number times the displacement or some coordinate, you're going to have an oscillating system. It might not be a spring, but it's going to act like a spring. Now, what is this constant K? Go ahead and make a note of it. It's not on the outline, but constant K is known as the spring constant. And the spring constant is a number that tells you how stiff the spring is, how hard is it to stretch it or compress it. Okay? And it's measured in newtons per meter. So if you have a spring constant of 100 newtons per meter, that means it takes 100 newtons of pull to elongate it a full meter. But if you have a spring constant of 5 newtons per meter, then that means all you need is 5 newtons to extend it 1 meter of distance. Now, most springs don't, I don't even know if anything that NASA has extends a meter. But the point is that if you have a big spring factor, it's tough to move it a millimeter, it's tough to move it a centimeter, it's tough to move it any distance. Smaller means easier to move it to squish it in, compress it by a millimeter, or extend it by a millimeter. To squish it in by a centimeter is tougher or is easier for a small factor of K. All right. Now, here's another, so that's the force law, and with forces we want to also think about work. Now, the work formula and the potential energy formula is completely different. SP equals 1/2 kx squared. Those of you that have had calculus, do you see an integral here? See it? Yeah, this is an integral. For us guys, don't worry about the calculus. Just write that down. And this one is special. 1/2 K. It's a little bit different from gravitational potential energy at the surface of the Earth. That was just minus mgy. All right? It wasn't second power in y. This one is the second power in x. All right? Or you know, if you have a hanging spring, a hanging oscillator, it'd be second power y squared. Okay? But this one's an x horizontal oscillator. 1/2 kx squared. So the upshot for us is the following. Anytime that we see a restoring force proportional to the displacement of any coordinate or of any dynamical variable, there's going to be oscillation. Or if we see the potential energy, Sedora, proportional to the square of a coordinate, you know, like this 1/2 kx squared, you know, and you know our gravitational potential energy, it didn't look like that. It had minus mgy. That's not a oscillating system. It's just a, you know, gravitational system, a system of surface of Earth. That's, you know, the baseball parabola. That's not a oscillating system. But if you have something with if you have something with a number times a square of a coordinate or a square of just about anything, always think oscillation. And we're going to talk more about that as we go. So those are the two signs: a restoring force proportional to the coordinate, or potential energy proportional to the square of the coordinate. Okay? Always will give you, they always come together, and you might spot one before the other. You know, your measurements of energy and work and kinetic energy and stuff might lead you to say, oh, I got a 1/2 kx squared here. Or you might be measuring accelerations, in which case you might see, oh, I got a minus kx here of some kind. And students, we physicists see these everywhere. You know, we study springs, and, you know, we talk about, you know, restoring force and, you know, oscillation and sines and sinusoidal rhythm and stuff like that, like we have today. But it's actually, you know, molecules. We use this model for molecules and atoms. You know, and I dare say that those guys that are trying to model the Arctic oscillation up there in the Arctic, they're probably trying to figure out some kind of restoring force, except it's very difficult. I mean, that's a huge system. You know, thousands of miles, you know, so it's basically going from eastern Siberia all the way over to Greenland and Hudson's Bay. So that's thousands of miles. And the time scale is measured in months for that thing. It's, you know, over the course of a year or more than a year or so. Very difficult, but I'm sure they're probably trying to find out why it oscillates. So let's keep going. Oscillating system means you do a repetitive motion. You know, this, you know, circular motion is an oscillating system. We just talked about that. So you start at the top, you go to the bottom, go back to the top. Down to the bottom, back to the top. Down to the bottom, back to the top. Down to the bottom, back to the top. Always on the same path. If it's uniform circular motion. Now for a spring, it means left and right, left and right, left and right, left and right. Left, equilibrium right. Equilibrium left. Equilibrium right. Equilibrium left. Etc., etc. So it basically means 4 journeys to or from the equilibrium position. Here they are. Okay, A, B, C, and D. All right. If you start at equilibrium, and image B here shows me that I'm at instant A, in photograph A or image A, the object is moving to the right. Okay, so it's moving along this path out to maximum extension. So image A, the position of the object is at equilibrium. and it's moving out this far. Okay? And it stops. So write down V equals 0 for image B, because that is maximum extension. Okay? That's as far as it goes. And here's what happens. The kinetic energy that it had at equilibrium is all gone because of the restoring force. The restoring force has stopped it. And now the restoring force is going to bring it back to the left. Okay, so here's my next restoring force. Now I've got maximum leftward motion. I've got a leftward restoring force. So I'm accelerating back towards the center. I'm getting faster and faster. All right, and I get to the center. Okay, now here at equilibrium. So image C, I'm back at equilibrium, but guess what? I got a lot of kinetic energy because of the spring. Okay, the spring is dragging me back. I mean, the object here, out here, was stopped. And then it started catching leftward newtons. So leftward acceleration. And so right here, it's got as much leftward acceleration as it's going to get. And so it's at maximum kinetic energy. So make a note, maximum kinetic energy at equilibrium. If it has any kinetic energy, it'll be maximum at equilibrium. But you know, the thing is, it's just going to keep on going. But guess what? Now, when it ships a little bit to the left of equilibrium, guess what? It's going this way, but it gets some pushback force. Now it's getting rightward newtons because it's a spring. You compress a spring, bang, you get pushback force. In this case, to the right. So it gets out here to so this leftmost point in the motion, that's maximum compression. Okay, we've compressed the spring as far as she'll go. We've converted all the kinetic energy. It had a bindle of kinetic energy, so like 5.7 joules right here at equilibrium. And now out here, it's got 5.7 joules of potential of 1/2 kx squared. All right? No kinetic, all potential. So write a note to yourself, max compression, max extension, 1/2 kx squared is maximum. Spring potential energy is maximum because x is maximum. Or I should say the square of x is maximum. Okay? Because remember, x is negative over here at max compression. So this might be, x equals negative 0.21 meters, for instance. But in the potential energy formula, you square that number. So you still have the same amount of joules of potential energy here as you have over here at max extension. And now you're at maximum extension, you're stopped for just an instant, and then guess what happens? Bing, back to equilibrium. And there are the 4 trips to or from equilibrium, a full cycle of the motion. So that is one way to describe an oscillating system. Now this is a cinchy, one-dimensional spring system. But we studied all, atomic systems that have oscillations in more than, that uniform circular motion, that's oscillations that are identical but different directions, perpendicular directions. We could do that, at the wazoo if we need to. It's tricky, but we can do it. Now, for reasons of mathematicians and scientists in general being lazy, and for reasons of having used trig and calculus at the wazoo to get like spring potential energy equals 1/2 kx squared, that results from calculus. It's easier for us to describe the motion of the wave or oscillating system in terms of the amplitude when you define the amplitude as the size of any of these 4 black arrows. All right, so from equilibrium out to max extension is the amplitude. So instead of using max extension to max compression, it turns out to be a little bit easier, not too bodaciously easier, but still for slacking and lazy bone mathematicians and physicists, half of that distance, the amplitude, ends up being easier to use. So if you don't have a fractions and stuff, and works out nicer. Now, here's a picture. This is a picture that shows you amplitude vectors. Okay, position vectors, the length of the amplitude of the system. Now, here's another kind of idealized picture of a wave in the ocean. And a wave in the ocean is basically an oscillation above sea level and below sea level. So just draw in sea level, this kind of blue streak here. And this is what an idealized ocean wave looks like. You get a peak up here, and here's another. So I got 3 peaks, and I got 3 troughs. Okay? And so this is the calm sea. So if there wasn't any wind, you'd have the blue streak. But if you get a little bit of wind, you get some waves going. All right, big or little. And this distance here from sea level up to the top is the amplitude. All right? And here's another diagram of the amplitude. This distance from sea level down to the bottom of the trough. All right? So those are amplitudes. And we'll have another diagram here in just a second. Because it's circular motion. This baby that we were just working on? Yeah. The amplitude is just the radius of the circle. How far away from the equilibrium position do you get? 0. Well, that's just 1 radius to the right or 1 radius to the left. 1 radius up or 1 radius down. All right. So in this system, the amplitude is just the radius. And, if you're working on some other system, we sometimes get systems where an ellipse has formed. Yeah, you can still work with this. Now, I want to get down to some basic specs for waves, because waves are a special kind of an oscillating system. Spring is just kind of sitting there, moving something left or right. But here's a spring system that you can make waves travel in. A slinky. If you take a slinky and you shake it, a little bit of shake will go from your hand to the other end of the slinky, and then it'll come back at you. So that's a simple wave system. Now here's one of the main important things about waves. And this is an outline now. And waves transport energy and momentum across space-time, but they don't necessarily transport atoms and molecules. So, for instance, if there's a storm on the eastern Atlantic off the west coast of Africa, and if there's a big storm over there, we'll sometimes get waves all the way over here. Maybe some good surf. Okay, now those waves transport energy and momentum from the coast of West Africa all the way to Cocoa Beach, so you can go out there and surf. But when you're out there on a wave that started in Africa, off the coast of Africa, and you're riding it at Cocoa Beach, those water molecules are not from Africa. They came up through the Gulf Stream. All right? So, the waves are coming from, but all the little plankton, all the sharks and other fish and jellyfish and stuff in the water, it doesn't move with the wave. The wave is moving energy and momentum, not matter, not usually. Waves will move a boat around, it'll give it a little bit of impulse in a certain direction, but not, It doesn't, unless you're on a surfboard, then you move with the wave. You're getting some newtons from the slope of the wave. But normally speaking, the matter doesn't move with the wave. The other thing is it's not easily localized, all right? So you have to ask yourself, well, what's the GPS address of this crest of the wave? So is that the location of the wave? Well, no, because you could just as easily say, well, this trough in the wave right next to it, peak and trough, how about the GPS of that? And a trough in the waves is elongated in some shape, maybe 50 yards, maybe longer. All right? So which part of that trough do you take the GPS of? So the whole idea of localizing a wave is a little shaky. But here's something that we do figure out. We figure out different parts of a wave and different parts of a wave train. Now, one of the things about a wave is they always have a propagation speed. They're moving. A wave is something that moves. So it's carrying kinetic energy and momentum from point A to point B. So it's going to have some kind of a velocity vector. And it might not be that bodacious, but, they don't move. Although I've heard that like tidal waves, tsunamis move really fast. As fast as a jet plane. So that's a pretty big propagation speed. But the thing about a wave is, both peaks, everything's going to be in sync. So this point at sea level, it's going to be moving to the right, whatever the speed is, 2.7 meters per second. And this trough down here, So a wave is going to have everything moving in concert, ideally speaking, in one direction. Now you can get waves to speed up and slow down, for instance, as you go from deep water into shallow, from cold water into warmer water, and your eyeglasses, if you're wearing specs, the speed of light changes from air into your glasses, the plastic or the glass that you have for your specs, and then it changes again when the light comes out of the glass and back into the air. And then it changes again when it goes into your eye, through the lens in your eye. All the time, hopefully, if your eyeglasses are good, brings things to a focus. But those light rays that go into your specs, they change direction slightly. They're still going at the speed of light, but they change direction a little bit. And your eyeglasses give just enough change of direction to focus the light rays on your retina. And if your eyes, if the built-in lenses in your eyes focus well enough, you don't really need glasses. Okay, but if your built-in lens, the one that you were born with, focuses a little bit behind the retina or a little bit in front of the retina, then you need some specs. All right. Now, another part of a wave or another idea is the phase. Now, the colloquial terms are peak and trough. Those are the easy ones. And, you could call this right here the middle or the 0 point, and this is one that's descending where the wave is going from high to low. Okay. Another thing you can do is use a number between 0 and 2 pi. And the reason for that is the circumference of a circle. We relate it to periodic motion. Okay? And periodic motion, the simplest case, is circular motion. The radius of a circle times 2 pi is the circumference of the circle. So if something's going along the circumference in a periodic manner, numbering it with 2 pi or symbolizing it with 2 pi is a normal thing. So if you make the peak up here, if you make this peak 0, then halfway through to the next peak is pi. So this first trough is, you would assign the symbol pi. And then the next peak up here, that would be 2 pi. And then the next trough, 3 pi. And then the peak after that, 4 pi. Or you could just start numbering over. 0 pi, 2 pi. 0 pi, 2 pi. This part here, this 0 point descending corresponds to pi over 2. This one over here, I haven't marked it, but this 0 point ascending corresponds to 3 pi over 2, or half a pi. So this is half of a pi, and this is 3/2 of a pi over here. And then this is 2 pi up here. It's full 2 pi. Okay, now I didn't write it down in the notes, but add this to your notes. You can use degrees. And how many degrees do you have in a circle? 360. So if you choose the peak to be 0 degrees, then a 180 degree phase point is the trough. And then this 0 point ascending is 90 degrees. And this 0 point ascending is 270. And this next peak up here, 360. All right? A full circle. Now, another part of a wave from 2 consecutive phases, so peak to peak, is called wavelength. The distance, this is measured in meters. So peak to peak, or, like here, I'm going ascending, 0 point ascending to the next 0 point ascending. So this is from 270 over here in this wave, and 270 degrees over here in this part of the wave. All right, so that distance, or you could go trough to trough, pi to 3 pi. That's one full wavelength. Here's another one. 0 point descending to the next 0. So don't skip over to the next, 2 waves. Then you'll be measuring 2 wavelengths. But one full wavelength is that. Now, half a wavelength is sometimes an important quantity. So that would be this. So this is 0 point descending over to 0 point ascending. Half a wavelength. Or you could say, half a wavelength is from trough to peak to trough. That's half a wavelength. Trough to trough is a full wavelength. Peak to peak is a full wavelength. So trough to peak would be half a wavelength. All right, now, here's amplitude. We've already done this. All right? And now this here would be we don't usually use it in physics and stuff, but I think meteorology guys and the Weather Channel, when they're talking about wave height at Cocoa Beach, this is what they're talking about. It's basically double the amplitude. All right. I'm going to start talking about wavelets on Thursday and diffraction. Continue reading in chapter 7, and I'll see you on Thursday. There'll be some homework tonight, fairly small assignment. You're dismissed.